Dear students, welcome to the online class. I am Dr. S.S.C. Hiramat. In this video, you are going to study about the transition state theory. This theory was proposed by Eyring and Polanyi in the year 1935. This theory is also known as the intermediate complex formation theory. Intermediate complex formation theory. This is another name for this theory is intermediate complex formation theory, or this is also known as the activated complex formation theory. Activated complex formation theory. Means the transition state theory is also known as the intermediate complex formation theory or activated complex formation theory. This theory can be explained with the help of the energy barrier diagram. It can be explained with the help of energy barrier diagram. Suppose this is y-axis and this x-axis. Along the y-axis, that is energy. Along x-axis, reaction path or reaction coordinates. Okay, reaction coordinates. Now suppose this is the energy level of reactants, that is reactants, and this is the energy level of products. This is energy level of products. Now the reactants to transfer into product, they have to cross a barrier, that is energy barrier. Means they have to reach a high energy state and they have to come to the product side. Here the reacting molecules come closer to each other and form the intermediate complex, and intermediate complex has this much energy, that is activated complex or intermediate complex. Activated complex is formed here. Activated complex formed here. Now to form the activated complex, the energy required is this much. This is the energy of activation. Means reacting molecules come closer to each other and undergo number of changes and accompanying with the energy, and they occupy the excess energy and they form the activated complex. The activated complex may give the product. Suppose this is the energy of activation of reverse reaction. If the products are to be transferred into the reactants, they have to cross again the same barrier, that is energy barrier. Thus, according to the transition state theory, the reacting molecules come closer to each other and undergo the number of changes accompanying with the energy changes. Then the reacting molecules come closer to each other and form the activated complex or the intermediate complex. The activated complex is unstable and it dissociates to give the product, or it may dissociate back the reactant. Okay. Now there is the equilibrium between the reactants and the activated complex. And in this case, the rate of reaction depends upon only the concentration of the activated complex. In this diagram, this level shows the energy of the reactants, and this level shows the energy of products. And difference between them this is energy change of the reaction, that is delta E, energy change of the reaction. Now energy of the products is less than the energy of the reactants, therefore this much is the energy change of the reaction, that is delta E is positive. Here EA is the energy of activation of the forward reaction and EA dash is the energy of activation of the backward reactions. Now about postulates of transition state theory or activated complex formation theory. First one, reacting molecules approach each other and undergo changes accompanied with energy changes. Reacting molecules come closer to each other and form high energetic intermediate compound known as activated complex. Third one, the intermediate compound is unstable and dissociate to give products or dissociate to give back the reactants. Fourth one, there is an equilibrium between activated complex and reactants such that the reactants give the activated complex and activated complex give back the reactants, and it is governed by one equilibrium constant K star. Then fifth one, overall rate of the reaction is proportional to the concentration of activated complex, means rate of reaction is directly proportional to concentration of this activated species. Then last one is the definition of activation energy, that is activation energy, that is EA is the minimum excess energy acquired by the reacting molecules to form the activated complex. Now consider a bimolecular reaction. Consider a bimolecular reaction that is A plus B gives one intermediate complex, that is AB star, which gives products. This is a bimolecular reaction, and according to the postulates, there exists one equilibrium constant K star between reactants and intermediate complex, and K is the rate constant of the reaction. Okay, where K star is the equilibrium constant and K is overall rate constant. Then K star is equal to concentration of AB star divided by concentration of A into concentration of B. Okay, then from this it shows that concentration of, that is AB star, is equal to, that is concentration of AB star, that is intermediate complex, is equal to equilibrium constant into concentration of A and concentration of B. Suppose this is equation 1 and this is equation 2. Overall rate constant of the rate of the reaction may be expressed as overall rate of a reaction may be expressed as rate dx by dt is equal to rate constant K and concentration of reactants A and B. Suppose this is equation 3. This is equation 3. Now, according to one assumption of the transition state theory, rate of reaction is proportional to the concentration of the activated complex. According to one postulate, of the theory, rate of the reaction is proportional to concentration of activated complex that is AB star and proportionality constant is known as frequency factor. Therefore, rate is equal to dx by dt is equal to frequency factor into concentration of activated complex. From equation 2 and 4, rate equal to dx by dt, that is equal to frequency factor into equilibrium constant into concentration of A and concentration of B. So this is equation 5. From equation 3 and 5, equation 3 and 5, this is equation 3, that is K into concentration of A into concentration of B equal to frequency factor into K star. That is K equal to frequency factor into K star. So this is equation 6. Frequency factor may be taken as frequency of the vibrational energy, vibrational energy, vibrational energy, E, according to Planck's equation, E vibration equal to h nu, which may be equal to kT, for one molecule, where K is Boltzmann constant. K is Boltzmann constant. Therefore, mu equal to kT divided by h. kT divided by h. We know kT, k into Avogadro's number, that is equal to R, or 1 mole, Then equation 7 becomes equal to k T into Na divided by h into Na, that is equal to Rp divided by NH, where Na is Avogadro's number. Equation 6 and 8, we get K equal to this frequency factor equal to nu, that is Rt divided by NH, and K star. So this is equation 9. From thermodynamics, equilibrium constant and free energy change are related by equation delta G star equal to minus RT ln K star. Equation 9. On rearranging, just you divide this by T, then R ln Kp equal to minus delta G star divided by RT. then A star is equal to e raised to minus delta G star divided by RT. So this is equation 10. We know delta G star is equal to delta H star minus T delta S star, means according to Gibbs-Helmholtz equation. Here we can substitute delta star equal to this value, delta G star equal to, according to this we are going to get this. Suppose this is equation 11. From equation 8 and 10 we get K equal to RT divided by NH into K star equal to e raised to minus delta G star divided by RT. So this is equation 11. We know from Gibbs-Helmholtz equation, we know, or from Gibbs-Helmholtz equation, that is delta G star is equal to delta H star minus T into delta S star. This is equation 10. 12. From equation 11 and 12, from equation 11 and 12 means just to substitute the delta G star into this, then you are going to get K equal to RT divided by NH into e raised to minus delta H star divided by RT into e raised to delta S divided by R. Delta S divided by R, that is e raised to del, that becomes plus delta S star divided by R, means just by expanding e raised to delta H star divided by RT, you substitute this delta this into this, then this minus and this minus gets cancelled, and the T divided by RT also gets cancelled. So this is equation 13. Equation 13 is the expression for rate constant in terms of enthalpy and entropy. This equation is applicable to bimolecular as well as unimolecular reactions. Unimolecular reactions. For the reactions in solution, in liquid solutions, enthalpy of activation delta H star may be taken as equal to internal energy of energy of activation, that is delta E star. Then equation 13 becomes K equal to RT divided by NH into E raised to minus delta E star divided by RT, delta E star divided by RT into E raised to plus delta S star divided by R. On taking logarithm, log ln, that is taking ln, we get ln k equal to ln RT divided by R divided by NH plus ln T plus, that is not plus, it remains as it is, minus delta E star divided by RT plus delta S star divided by R. On differentiation, suppose this is equation 15. That is equation 15. On differentiation, of equation 15, we get 15 with respect to t. Differentiation with respect to t, we get d ln k divided by dt is equal to, then differentiation of ln r divided by nh, r is constant, n is constant, h is constant, and that becomes equal to 0, that is equal to 0, plus differentiation of ln t equal to 1 divided by t, and differentiation of, that is delta E divided by RT is same as differentiation of 1 divided by t, that becomes equal to t square, and that too minus becomes plus. Then differentiation of this delta S is that is there is no temperature term in this equation, that becomes equal to 0. Then equation, suppose this is equation 16. This equation becomes d ln k divided by dt, that is with respect to temperature T, is equal to, this term gets cancelled, this term gets cancelled. Now we may take RT square as common. Then delta E remains as it is, delta E star remains as it is, plus 1 divided by T, that becomes equal to RT. That is equation 17. Now, from Arrhenius equation, we have, that is K is equal to A e raised to minus EA divided by RT. Taking logarithm, taking ln, we get ln k is equal to ln A minus EA divided by RT. EA divided by RT. Suppose this is equation 18. On differentiation of equation 18, on differentiation of equation 18 with respect to temperature T, we get d ln k divided by dt, differentiation of this. Then differentiation of ln A. Ln A is constant, RNS constant. Then differentiation of constant, that is not equal to 0. Then differentiation of this, that is EA divided by R, remains as it is. Then differentiation of 1 divided by T is 1 divided by T square, and that minus becomes equal to plus. Minus becomes equal to plus. Then suppose this is equation 19. Equation 19. Now, from equation that EA, this delta E, RT, that is 17 and 19. From equation 17 and 19, which are differentiation of the rate constant with respect to T, and this is also differentiation with respect to T, rate constant with respect to T. Then LHS are equal means RHS are equal. Then you are going to get EA divided by RT square is equal to delta E star plus RT divided by RT square. That is the EA, that is energy of activation, equal to enthalpy of activation plus RT. Now suppose this is 19 and this is equation 20. Equation 20 is for a reaction in liquid solution where delta H star is taken as equal to delta E star. This is taken. Now, for other reactions, we want to apply the same equation for the other reactions. For any reaction, delta H star is not equal to delta E star, that is delta N is not equal to 0. We know delta H equal to delta E plus P delta Phi, that is delta star. Let us take all these as star. Then this is equal to delta E star plus delta N into RT. For the gaseous reactions, the change in volume equal to, that is, we can calculate delta N There is a change in the number of moles of gaseous products minus the gaseous reactants into RT. Okay, that is delta E star equal to delta H star minus delta N into RT. Suppose this is equation 21. From equation 20 and 21, we just substitute this value in this equation. We are going to get EA equal to delta H star minus delta N into RT plus RT. This equation is applicable to the any reaction, gaseous reactions or solution in the liquid. In the case of solutions, this becomes equal to 0. Now, we may apply equation 22 to the above equation, that is K equal to RT divided by NH e raised to minus delta H star divided by RT into e raised to delta S divided by R, the above equation. Now, case 1. Now, let us take the case 1 where delta N equal to 0 means the number of gaseous reactant molecules equal to the number of gaseous product molecules, so that delta V is also equal to 0. Delta V is equal to 0. Now, in equation 22, we get, that is EA equal to delta H star minus delta N into RT plus RT. That is, when delta N equal to 0, this term gets cancelled. Then you will get delta H star equal to EA minus RT. EA minus RT. Delta H star equal to minus EA RT. Substituting this, suppose this is equation 23. Substituting equation 23 in the above equation, we get K equal to RT divided by NH remains as it is. Then E raised to minus delta H star is equal to minus EA. Then minus of minus becomes plus RT divided by RT into E raised to delta S divided by R. That is K equal to RT divided by NH, then E raised to minus EA divided by RT. Then this term, another term E, RT plus RT, that is the denominator, gets cancelled and that becomes equal to 1, remains as it is. Then E raised to minus delta S divided by R. Suppose this is equation 24, which is applicable to a gaseous reaction in which the delta N is equal to 0. Now, case 2. Here delta N is equal to minus 1. Minus 1 means the number of molecules of gaseous products are less than the number of gaseous reactant molecules. Definitely delta V is negative. Let us remove that. What happens? thing. Then equation 22 becomes that is EA equal to delta H naught 1 minus 1 up minus, that becomes plus delta N into RT plus RT. Okay, then we may rearrange this, that is delta H star equal to EA minus delta N RT, that is equal to minus 1 RT plus 1 RT, that is equal to minus 1 and plus 1, that becomes equal to 0, that is delta H naught equal to EA, only EA, that is delta N is minus 1 means it gets cancelled. Then by substituting this in this equation, suppose this is equation 24, by substituting this in equation 22, in the above equation, we get K equal to RT divided by NA e raised to minus EA, then minus RT plus RT gets cancelled, then e raised to delta S divided by R. So this is equation 25. Means equation 25 is applicable to the reaction in which delta H equal to minus 1. Similarly, we can apply the 22 equation to the any reactions, gaseous reactions or liquid solutions reactions, where there is the number of change of the molecules is different.